work on Fourier transforms. So, spectral method, if some of you are working on, you need some definition of Fourier transforms. Okay. So, Fourier space has very important advantage that you can see different scales. You understand scale, no? I said you have large scale, and I want to understand what happens at small scales. So, the idea, an example which I give all quite often is that there are structures at the government level, right, at the largest level, then the ministry level, then subdivision level. So, there are different levels. Finally, you reach district, village, community. So, these structures you can't capture if you have a real space, full real space. You can't solve equation which have 1 billion or 1 trillion variables, but it is possible to understand them at different levels. So, there are physics, in fact, there are connections, it is not that they are not connected, but you can abstract what happens at that level, then different level, but Fourier transform makes you lets you do that. So, these are, so when I have wave numbers, then I have its properties at that scale. So, we have waves, this one, then this one, tiny. So, it tells you that what is the energy at that scale, energy that scale. But if you are working in real space, you can say energy in real space will be energy here, energy here, energy here. So, you can say in real space division, Kanpur temperature, Delhi temperature, but I want temperature at different scales, you know. So, you want what is the average temperature at 100 kilometer scale, okay, of temperature. So, that will come from Fourier transforms. And I say, well, I want in 1 meter scale. If you measured it, you can get it by Fourier transforms. Okay. So, that is a very powerful idea, and it is really powerful idea. Of course, mathematics lets you solve some equations, but you should also understand what it means physically. Okay. So, the definition of Fourier transform is, so I given a function f(x), so I will assume it to be periodic. So, I am going to explain in terms of e to the power I k x, but you can easily generalize in terms of sin kx and cos kx as well. So, if the function is periodic from 0 to L, so you go back, this length is L, then you can write this as Fourier transform f hat of k bar, let me put k bar x. Now, what is k bar? K bar is a wave number which is defined as 2 pi by L times k. So, k is the integer. So, that is why I put k bar. So, this is a factor, and this you studied, no, that is a wave number. So, k will range from minus infinity to plus infinity, right. So, that is the definition of wave number. So, this is due to Fourier. Fourier said this. So, you have to sum, but it goes from minus infinity to plus infinity. Now, this series sum is quite a weird series. In fact, a lot of great people disbelieved it, like Lagrange did not believe it. Lagrange, Fourier, they were all contemporaries, 1800, after the French Revolution. There was huge energy in France, and they did not believe it because this is not like Taylor series. Taylor series we have sum ak xk, and if x is less than 1, then you can say yes, series will converge. But what is the guarantee that this series will converge? So, these are all mod 1. So, that was a major doubt. I mean, mathematicians like big guys, Lagrange was very powerful, Laplace said no, it don't work. So, he published this in a book, monogram. He is not published as a research paper, but later on, I mean, but the Fourier himself did not prove it. He did not prove the convergence. So, this series does converge. So, the idea is that if I have finite number of terms, n could be 100. So, convergence means that this n equal to 100, I get a representation of f of x, not exactly f of x. I put one more term, it will be better approximation. That is what it means by convergence, and it was proved by mathematicians later, Cauchy, and I think Cauchy proved this later. Okay. Anyway, that is mathematics of Fourier transform, is very, very useful, and it is very interesting math. I can invert this very easily. So, f hat of k bar is 1 by L integral f x minus I k x dx. Now, this is for real space. That means x is continuous, it goes from 0 to L, and k is infinite. Now, in computer I can never do this x to be continuous, it is not possible. So, idea is to discretize this x. So, I discretize them at n points. So, I can make a line with keeping in mind that this is same point as that. Okay. So, we do not store the last point, because that is same as the first point. So, I make n divisions. So, my delta x will be L by n, and so what is x j? So, index of the or coordinate of the point j. So, its coordinate will be x j, real value, and that will be j times delta x. So, that will be L by n, and I will make j vary from 0 to n minus 1. So, that takes care that I will not have L. Okay. So, now for I need to discretize it. So, this sum remains as this, but this sum will become, this integral will become a sum. So, now this is going to be a sum 1 by L. Now, dx I can take outside, is L by n f j for I. Now, k is, what is k? That is a definition, k bar actually, these are k bar. K bar is 2 pi by L times k, and x will be coming from here, x j. So, I have to sum x j will be j L by n. So, the integral becomes a sum, no, this is you learned from your calculus course. So, interestingly, a lot of things cancel, L cancels, this L cancels. So, I get 1 over n sum f j, j goes from 0 to n minus 1, exponential I 2 pi k j by n. So, that is how I compute f hat k. This is Fourier amplitude. Now, it is a complex number, this f, this is complex number. My f x can also be complex. I will restrict most of my discussion when f x is real, but for Schrodinger equation psi is complex. So, you can use complex f. Now, this also some, this k x, k bar x will also be replaced, since I am working with discrete x. So, this also will be replaced. So, let me write this f of x. Now, this f of x will be f j. So, f j will be sum this k f k, k bar is index is same as k index, because this is a constant, e to power I, k is 2 pi by L k, and this is L by n. So, exactly same thing, this cancellation will happen. I made a sign error, no, this is a minus sign here, and this is 2 pi by n k j. So, our notation is that for going from f k bar or f k to f x, I have plus sign, and going from f x to f hat, I have minus sign. That is our notation. Some books flip it, but that is how we follow this notation. Okay. Now, in this case, I have how many real variables? I mean how many real space variable, I should not say real variable, real space variable. F could be complex. So, there are n of them, n f j's. Huh? No, I do not keep the last point, because that is same as the first point. So, you keep only 0 to n minus 1, so which is somewhere here. So, how many Fourier variable must be? How many k's should be there? So, the number of k's must be again n, because this is a linear transformation. You can write this in terms of matrix. If it is a very interesting form, so this becomes a matrix. This is f, let us make f0 f n minus 1. So, this must be also, if you want one to one mappings of this to this, it also must be n variables. So, my f hat k should also be n of them. That is a different, discrete Fourier transform will limit you to only n k's, not infinite k's. So, this will, I can label now, by the way there is one interesting property, this definition you can easily show that f hat of k is same as f hat of k plus n, right. So, in this if I add k to k plus n, 2 pi j will come, which is 1. So, this is the property. So, I can choose my starting point to any k. So, I can say my k goes from 0 to n minus 1 for k, or you can say minus n by 2 plus 1 to n by 2. Okay. So, given f0 fj's, I should be able to uniquely determine f k's, f hat k's, otherwise Fourier transform will not be defined. This is not a good definition. So, this is a linear transformation. So, number of variables unknown must be same as, I mean this is a matrix equation, right. So, whatever is here should be here, and determinant must be equal to 1, non-zero, and indeed you can check the determinant made of this pi 2 pi n. So, k will go to 0 to n minus 1, j will go to 0 to n minus 1. You can define this transformation, otherwise you cannot define this transformation. This matrix will become some longer matrix, I mean there will not be a n by n matrix. So, I want unique transformation from fj to f hat k and vice versa, and that is possible only if this has n variables and this has n variables. That is property of linear equations. Of course, I want the determinant to be non-zero. Okay. So, this is all guaranteed because this determinant is non-zero. Okay. So, we use this notation, but so there is very famous library called FFTW, okay, fastest Fourier transform in West. This is a parallel library. We have developed another library called FFTK, that has separate property I can't do in this course. This is a parallel, so you want to use in parallel library, K for Kanpur, okay, that is what we did not think of better name. So, this is for parallel library for using many processors. So, this I can't teach in this course. So, FFTW has a very strong influence on the notation. So, they use this notation 0 to n minus 1. Okay. You can always convert. So, you can using this property you can always convert, but in the today's class I will keep this in mind. So, when you are working Fourier transform you have to be careful what is your wave number. So, the reason why we like to physically understand this is the wave number is property of the waves. So, it corresponds to wavelength which is L by n by 2, that is why, okay, that is why you should use that. Okay. Now, this is for 1D Fourier's 1D complex variables fx. I want to use only real variables. like velocity is a real variable. If you solve for velocity in one of the projects, you will get real variable for f, if f is real. If f is real, then it has a some more interesting properties. So, in fact, it is quite easy to see in this equation. No, which equation? F, where is f hat k? This equation, f hat k. So, k and k bar are equivalent by this multiplication. So, you can, what about f hat of minus k? So, you will be 1 by n f j minus 2 pi minus becomes plus k j by n, right. What about complex conjugate of that equation? So, f hat of k star is in fact exactly same as this, because f j is real. So, the complex conjugate of this is same as itself. So, it turns out these two must be equal. Yeah, so I said if f is real. So, this property must be satisfied. That means I do not need to store all so if f is real, then how many variables I got. So, that counting is required with when you do discrete transforms. If f is real, then all these guys will be real. How many variables will be there? N. Now, please remember the complex has two numbers, real and imaginary parts. So, this is n real numbers. In my earlier definition, I was assuming that n to be complex, these were all complex. So, if this is real, then this must be only n real numbers. If I have more than that, then it is a problem. N real numbers, okay, not n complex numbers. If f is real, then n fj's. But now I should have only n real numbers in the for f hat k. Now, you can easily show that this property, I will not belabor on it, but you can just do this algebra. Because of this property, these guys will be related to that. Now, this is the tricky part, 0 to n by 2 and this is minus n by 2. So, if I know this value, let us say 3, then what is f of minus 3? It is complex conjugate of this. So, I do not want to store these. So, I do not store any of the left values, the negatives are all connected. So, you do not store any of the left values, you store only these. Now, how many of them are there? How many real numbers? So, 0 to n by 2 complex numbers. So, number of real numbers will be n by 2 plus 1, you have to count this as well, okay, times 2. So, that makes it n plus 2. So, it looks like there are n plus 2 real numbers for storing f hat k. Is that clear? But there is a contradiction, right, because I have only n fj's, but I have n plus 2 complex numbers. Now, there must be some mistake I am making. The mistake I am making is that there are two values among these are purely real, they are not complex. And which ones are purely real? f0 is purely real. Why? It is average. f0, f hat 0, so this becomes 1. So, the 0 component Fourier space is just the average of all fj's. So, say f is real, fj is real, then f0 must, f hat 0 must be real. So, this is real. You can also show that this is also real. It comes with plus minus sign, this becomes a plus minus e to the power minus I pi j. Okay. So, this corresponds to f0 minus f1 plus f2 plus 1. So, it comes with. So, both are real. So, now everything is in order. So, indeed we have n by 2 complex numbers, but 2 of them are purely real. So, what is done in standard Python library is that for real numbers you should use RFFT. I will demonstrate some examples. You should use RFFT, and RFFT will give you, so this for R means real. So, it assumes that f is real, this f is real. Okay. Now, there is no project in which you are doing spectral transforms for complex numbers. Okay. So, we start with 0 and go up to n by 2, but in the library all of them are chosen as complex numbers. It is too much of a programming issue if you make some of them real, some of them complex. So, all these numbers are complex throughout, but when you are doing the calculation you should keep in mind that these two are purely real. Okay. So, that is a thing you have to remember. Now, this for 1D, all story finished. These are all called, okay. Now, just one more little point. This is a math. Now, how to do computation of this object, these two in computer. Now, nobody does this sum. Now, this sum for every k, how many sums are there? I did mention that in the class, in last class. This will have n operations, right, n multiplication, fj multiplied by this complex number. Now, I have to do this for every k, so there will be n squared operations, which is huge for when n is large. There is a very clever scheme that instead of doing this, we divide into odd and even parts. Okay. So, if I have something like I want to do Fourier transform 8 numbers, so 0 to 8. So, idea is to make 0, 2, 4, 6 and 1, 3, 5, 7, you divide into this, and there will be partial sum of this and partial sum of this. Now, we can add them and I will get this, but then you say, well, I can also divide this further into 2 parts. Okay. And so, there is a recursive tree which is made, and you basically, if you know how to do for the even part and odd part, then you can compute the full part. So, this is called divide and conquer, and using this one can do this in n log n. So, instead of n squared is n log n. In fact, the factor is 5. Okay, this FFTW, people are trying to make it even smaller, more work, but it can be done. So, this 5 is free factor, and this algorithm is called FFT, fast Fourier transform. And this is Kali-Tukey spelling, I hope I am right. Okay. So, I think this again comes from MIT. Okay. So, these are way back in 56 or something, 1956. So, you do it this way and it is fast, that is why it is called fast. Instead of n squared you do in n log n. You can read this if you like on more details on that. So, this is for 1D. Now, we can do for 2D. So, you have 2D data or 3D data. So, how do you do for 2D and 3D? Is that clear? Everything is clear for 1D? So, I have 2D real space data. Let us assume that we have real space data. Okay. So, for convenience I will make it n squared. So, this is x axis. So, you can think of a plate on which you have electric potential or temperature of the plate. Okay. Now, this is actually in real space this will be going from 0 to L, let us just make it 0 to L. But when I have to work with computers, I will discretize this. So, I will have only discrete things like this. So, for we can actually you can make it Lx, that is not a big problem, Lx Ly, this is Nx and Ny. So, what is the definition of transforms? So, I will just work for 2D. So, Fxy is the two sums. f hat of kx ky e to the power I k bar dot x bar x not x bar. And what is k bar? K bar is a vector whose components are 2 pi by Lx times kx comma 2 pi by Ly ky. Kx and ky are integers. It is just a simple generalization of 1D to 2D, and I can invert it. Okay. So, invert will be 2 integrals. Okay. So, we can exactly generalize 1D to 2D straightforward. Now, how does it look like in terms of discrete transforms? So, x y will not be continuous anymore, it will be discrete. So, we call them Fij. Now, there is one notation issue, this I will mix with this I. Okay. So, this square root of -1, but this is array index. Okay. No, is standard followed in textbooks. So, this is f, and now these are integers. So, kx, ky, exponential I. Now, again following the same idea. So, Lx by, so this becomes 2 pi by nx kx j, kx times I is the index along this, and this index along j, plus 2 pi ky j by ny. Okay. So, this is a you have these things. Now, we can write down what is f hat kx ky. So, it in fact is very similar, f hat minus of this. Okay. So, that is these are the definition in this called, okay, I must also, this is called DFT, discrete Fourier transform. Now, please note one important point, that here length does not come into picture at all. Okay. There is no length here, length has disappeared, it is only function of n, capital N. Now, it is a for you to think about, how does the length come in your spectral method? Some of you are working in spectral method. How does length come into in your equation? Fourier transform is neutral on L. Okay. So, please think about it, I will not tell you the answer now. Okay. Now, here also L does not come, it is off. Now, the question is, how do I store it? So, FFTW will spit out numbers, and you have to make sense out of those numbers. So, the numbers will come out to be, again I assume that f is real. So, f is real, then how many kx and ky will be there? Okay. So, this is, let us assume that these are n square number. So, now I will assume that nx equal to ny. Okay. Now, this will be again should be n square numbers, again otherwise there will be a problem. So, how it is stored? So, this one is how it is stored in computer. If this goes from 0 to nx n minus 1 or nx minus 1 along x direction. Now, you can generalize this property for 2D, this for 1D, or in fact any dimension. F at k is sorry, f at star of k is f at of minus k. K's are vectors, no? These forms a vector. Well, this is very similar to what you do in solid state physics, right? You what is Bravais lattice and is identical formalism. This is in fact the Fourier transforms. Okay. So, I am sure you know about this, but I mean you need to think a little bit more about this stuff. So, if this is the case, then I do not want to store the negative ky's. So, in this space, the lattice space I think is called, I am not sure what is it, it's called lattice space, space lattice. So, what is, you should think like this. So, I will rechange it because of this, again this property. So, you will work for each component. You can just see that for each component. So, kx equal to like this, it works this one. So, actually what I am going to do is, so this is not a convenient thing. So, you just store this by nx by 2 and minus nx by 2. Now, if there is a wave number like this, which is component kx, this is kx and this is ky, and this is ky, then there must be a number somewhere here which is minus ky and minus kx, correct. So, you do not store it because that is complex conjugate. So, we do not store anything which is negative ky. So, we basically cut off half of them, and this goes from 0 to ny by 2. Okay, there is bit of more variables here, but this detail I will not tell you. If you have proper counting in all has to be done, it must be same number of variables, n squared here as well as n squared in real, but that is a detail which I will not discuss right now. So, we store only the upper half. There is one group which is doing the project. So, for them I did mention them that, remember the reality condition, this is called reality condition. So, I will not tell you exactly how to get n squared here, but there is one part that if I have some variables here, let us say this one, then there is a variable which is wave number k, this will be minus k on the same line, right, this is ky is 0. Now, these two numbers must be complex conjugate of each other. So, this will tell you that you should not store these as well, but that is too much of a programming hassle if you do not want to store this. Your array must be 2D array, proper dimension. So, you store them, but you have to make sure that they are complex conjugate. So, this reality condition is a very important condition which must be imposed on the variables, otherwise my temperature will not be real. Okay, so, same thing is done for 3D. So, is it clear how 2D will? So, 2D computer will give you this. In 3D is going to be so these kx and ky also will be like that. So, it is a cube, but you do not store again the bottom lower half, you do not store it even in 3D. So, we can do in Fourier transform in any dimension including 4. Okay. So, I think in this class you probably need one in 2D. So, homework will be based on 1D and 2D. Okay. Okay, so let us see some examples. Okay, so what was defined for this project in this code? You want to come this side? It's still there 10 minutes. So, our functions are part of NP NumPy. Okay. So, FFT RFFT is what we will use. RFFT is part of FFT library. The FFT also has complex to complex definitions, but we will use only the real part RFFT. Okay. If you are doing Schrodinger equation, then you should not use RFFT, we should use something else. So, 1D transform, this is a syntax. So, I had to give an array A. So, he has made a nice function. So, forward transform. So, you do not need to remember syntax. So, transform given an array A which is 1D array and size, just give that, it will return the Fourier transform. Okay. So, this is the syntax np.fft.realFFT A by nx. Okay. Now, if you want to do, so that is for forward transform and inverse transform. Inverse transform you just put I RFFT, there is I sitting here. Now, for 2D, So, there is IRF, so there is just you have to put in the number 2, and for NDFFT you have to put n. Okay, n means it could be 3, 4. So, from the array A it will figure out what is the dimensionality of the matrix. Okay. So, if you want 3D, this is a you transfer A, but well anyway. So, you can use this syntax. So, we divide by n because by definition there was 1 by n sitting here. So, we this follow, in fact follow this notation 1 by n. So, this is how it is divided. So, Python FFT does not divide by n, but we divide by n. Okay. And here is multiply by nx. I think the definition is just reverse for what we do, that is why it is multiply by nx. I am not 100% sure. Okay. So, this is our definition, this will exactly give what I done in the class. I think this part you do not need to worry about it, this is for some other library. So, I will just show you one example how to call it and see the result. So, let us look at for 1D first. So, I am commenting this part. Okay. So, 1D I define the size 256 and my function is this is my function 2 cos 2x. So, what is the wave number where it is non-zero? It is 2, k equal to 2, Lx is 2 pi, 2 pi cancels. So, that is interesting. So, box many of these methods use 2 pi as a box size. What is the advantage? So, 2 pi cancels and you get basically k integer, wave numbers are integers 1, 2, 3, 4 like that. Okay. So, we got integers like that. So, I can so this is my fx, this is my x, I divide in nx stuff. In fact, we are not worrying too much about this, this is not be used in this code. Fk is Fourier transform. So, I just call this fx and nx, but this in turn is calling NP library, NumPy library. Yeah. What? Lx is 2, I am choosing Lx is 2 pi, this is my Lx. Ls is period of fx, but this my code should also work for cos x. Okay. So, for any function which is period, so my box is 2 pi. If for box 2 pi, this will be corresponding to k equal to 2. Okay. Now, this Fourier transform, forward transform, and my result is here Fk. I can also get the energy. This called mod Fk squared is energy, right? Energy of the particular mode. So, this will give you an example. I want temperature at that scale, energy. So, this is a very commonly used function. So, let us run it. Okay, so run my FFT. So, it has run. Now, so I should why isn't it showing? So, it is somewhere behind. Plot is behind. Yeah. Okay. So, now you have to see this carefully. It is in log plot. So, this is, so there are two colors. Let us just look at the code. Red is my amplitude of the real part of the function. Fk is red, no, this one, and the energy is blue. So, these are the numbers I got. Now, like it looks, so I do not like the 10 power minus 34. In fact, they are too tiny, right? From this onward is too tiny. So, let us put a while limit. so that I do not see all this stuff. So, 1 e minus let us put 1 e minus 10 2, I know the answer is 1, but let us put 2. This is my y limit. Now, it looks slightly sensible, no? That is like, so my amplitude it is 1, it better be because it is 2 cos k x. If you do the Fourier transform of 2 cos k x, so let me just write this as well. 2 cos k x, let us put k, okay, is written as root over I k x minus I k x by 2. So, what is the amplitude? No, not 2, 2 is cancelled. So, amplitude is 1 and 1. For wave number k it is 1 and wave number minus k it is 1. Okay. So, this is a real function. Now, I am not storing, please remember that this is not going to be stored because of this notation, the negative parts are not stored. So, my only non-zero is k equal to 2 Fourier mode. So, what do I get here? So, k equal to 2 indeed is non-zero. So, I have put k equal to 2 here, 2. So, I get this, in fact answer is 1, but I do get some non-zero values here, okay, this non-zero value 10 minus 2, but since it is a DFT, a discrete Fourier transform, there are always some error. Okay. So, this is 1%, but this is an error. Energy is f square mod f squared. So, it is, so every mode, so this has energy 1, this also has energy, f 0 seems to have energy, because again summing up, no, this is like summing up the stuff. I feel, well, let me make one more remark, I have only to use 256 points, if I use more points then it becomes better, this will go down, but there is always some error in numerical computing and it quickly goes to 0. Okay. So, discrete Fourier transform will not give you exactly 1 for k equal to 2 and 0 elsewhere. So, is that okay? So, you can also make some complex functions. So, there is one function which we had made. So, this function which has combination of 5 and 11 x. Okay. So, he needs x because x is stored here. Okay. To define x we need x, because 5 times x. So, he is using this x array. So, where will be non-zero? What are the non-zero wave numbers for the Fourier amplitudes for this? So, which k? 5 and 11, and amplitudes will be 2 or no 1, because 2 will cancel, 1 and 3. So, 1 and 3. So, we run it. Okay. So, 1 and 3, sorry 3 and 11, right, amplitude is 1 and 3, but the answer is for k equal to 5 and 11. So, this is 11 and this k equal to 5, 2, 3, 4, 5, okay, and energy is also following that. So, this is 1D, now we can also do for 2D. So, 2D program is okay. So, we are setting up here cos sin 2x cos 2y, right. So, sin 2x cos 2y, and we do 2D Fourier transforms, and is being stored as a is being shown as a p color plot. We can also look at the non-zero values. So, let us just see the color plot. Okay, so we are getting basically here. So, 2 comma 2, okay. This is coming because of, this is not correct, okay. This part is because of the reality condition and so on. So, this is put, so 2 comma 2, this is 2 comma 2, not a good color scheme, but it was cos 2x sin 2y. So, please figure out what are the non-zero values, where is the Fourier transform is non-zero. So, you can follow the same scheme, you have to write in as exponentials, okay. So, for which kx and ky it is non-zero, you can write, right, I mean sin is a product. So, this for the energy, this we put for energy. So, we can figure out which ones are non-zero. So, that part please work out. So, I can tell you what is that fk, no, fk 2 comma 2, this is one of the non-zero values, and its magnitude, this is a complex number, is this number, okay. So, you can always print which are the numbers which are non-zero, okay. So, you can also, there is a 3D example in the same code. So, that is about it, Fourier transforms completed.